Hello and welcome to our video about mineral accretion technologies. This is just a very basic and short overview of the technology and is not a supplement for the actual course. If you are interested in taking the comprehensive course, which covers chemistry, uses, technology, construction, and maintenance of these technologies, you can check our website at conservationdiver.com. Today we will cover some of the basics, but before we begin, we just want to say thank you to Correlate, which is an organization run by Robert Sevenster, and you can find out more about them at Correlate on Facebook. Bob has developed most of the technology that we are using today and has greatly accelerated this technology from where we were just a few years ago. The first thing to cover is what is a mineral accretion device. These are purpose-built structures that are deployed in seawater and electrified using low voltage DC current to create a process called a mineral accretion through electrolysis. This is an active form of coral restoration. In addition to creating artificial structures for securing corals onto, this allows for improved growing conditions for these corals by altering water chemistry. This allows the corals to redirect their energy towards other tasks and improves their growth rates and survival. According to published data, corals growing on a mineral accretion structure will grow 3 to 5 times faster. This also includes sponges, clams, and other calcium carbonate secreting organisms. Not only do these corals grow faster, but they can grow in a wider range of environmental conditions. This leads to greater coral reef health, abundance, biodiversity, and resilience. A higher fecundity or reproductive rate in these coral can also lead to larval replenishment in connected reefs. The structures also provides for habitat for fish and other coral reef organisms and is thus a complete form of coral restoration. As we discovered in our structure in 2010 during the global bleaching event, the corals on the structure itself survived much better than those on the adjacent reef, with less bleaching and less mortality. As you can see in these pictures here, the coral growing on the structure itself did bleach, but then recovered and continued to grow very quickly. This coral today is quite large and amazing. So back to seawater electrolysis. In this process, we're going to put down an anode and a cathode into the water and use a power transformer, generally from land, to power it and create the process of electrolysis. You may be familiar with this process from your high school chemistry class, as it's used to plate metals, remove rust, and other processes. Essentially, it requires putting 2 pieces of metal into water that is high in salinity. One of these metals, the positively charged N, was known as the anode, and the negatively charged N is referred to as the cathode. As electricity flows through the metal and the water, then different electrical processes occur, which changes the chemistry of the water. Well, the first thing that we'll see is that little bubbles start to form on the metal itself. At the anode, this is H2O breaking down and becoming oxygen bubbles, which rise out of the water. At the cathode, the opposite polarity, hydrogen bubbles rise out of the water. Due to the polarity of this reaction, anions and anions in the water will flow towards the different poles. The negatively charged will flow towards the anode, such as chlorine and hydroxide. The chlorine will then be emitted as chlorine gas, or Cl2. At the cathode, the positively charged ions will start to migrate towards the metal. This includes like calcium, sodium, and magnesium. As this process goes on, these start to accumulate onto the metal in the form of calcium carbonate and magnesium hydroxide. You really see this process going on as the pH of the water becomes more alkaline. these calcium carbonate minerals start to actually just fall out of the water. It looks something like this, which is a close-up of one of our actual structures. The little bubbles that you see are hydrogen bubbles, and the white film on the steel is calcium carbonate and magnesium hydroxide. This process happens actually quite quickly, as you can see in this series of photographs. On the left is the structures when they were put down, and on the right is the next day after the electricity has been applied for about 24 hours. What we see is the white minerals starting to accrete onto the structure itself. As these minerals accrete onto the structure, these are the same minerals that the coral uses to create its skeleton, which is a very high energy investment normally. With these minerals literally just falling out of the water around it, the coral is able to redirect its energy towards other tasks, such as stress management, reproduction, and reserves for the future. So back to the larger structure itself, it's quite simple. Essentially, we have the power, the cathode, and the anode. The power can come in multiple forms. Generally, we use land-based power as it's more reliable, which requires a step-down transformer to reduce the electrical load, and then a converter which changes the electricity from AC to DC current, which is then supplied to the anode and cathode structures underwater. If solar power is used, that is already created in DC, so it just requires voltage stabilizers and other ways to rectify the current itself before going to the cathode and anode. This technology has come a long way over the last 3 years through Coral Aid, and rather than using just simple battery chargers, we now have highly complex transformers, including magnetic switches that can be adjusted underwater, and voltage readouts, which actually are sent to cell phones and can be monitored 24 hours a day from anywhere in the world. The cathodes themselves can be created in any shape, size, or design depending on your imagination, from simple domes to more complex structures such as seahorses, viperfish, and any other structures that can be constructed out of steel rebar. Currently, we are using multiple anode designs. The metal is generally a platinum titanium alloy or a mixed metal oxide coated version of the same meshing. Multiple designs are available, and we are currently evaluating which ones are the most efficient. Although we have observed that this technology does increase the growth and health rates of the corals on the structures, there is still very limited scientific information published on the technology. And part of what we are doing at Conservation Diver is different research to increase the amount of available information and really evaluate how this technology can be used. One area we are doing that is on the island of Koh Tao with the Pyramid project, which includes several structures under different current densities with the same corals growing on them. This project began in 2016, and after another year or two should be published. Students taking our course will learn how to maintain, build, develop, and research mineral accretion devices, and will also receive certification in this device basics and techniques, and should walk away being able to construct their own mineral accretion device. Again, thank you very much to Bob from Coral Aid for developing this technology and working with us. If you're interested to join us, you can check out conservationdiver.com or follow along on our Facebook. If you really want to get involved, check out one of our training centers and join a course, and contact us for more information.